Welcome everyone to OX3C, Machine Learning Security. We're going to cover today a bunch of interesting topics, some of the more machine learning related aspects with background on machine learning models, how they can be used in security related operations, but also discussing mostly limitations of these models and how they fail. How models themselves can be stolen and different kind of privacy implications, along with also talking about privacy aspects of the data used in training for many of these models, and how they can be recovered and then result in unintended side effects. We're going to talk a little bit about adversarial attacks as well, how the output of models can be altered, and yeah, hopefully give you a bit of a glimpse into these underlying issues and potential pitfalls. I assume all of you have taken a machine learning class or two during your tenure as students so far. If not, this is not the class to go too much into detail. I'm sure you've been sharpening up on these skills for your future software engineering careers or just simple as users. But a very short definition here is that machine learning gives the computers the ability to learn without being explicitly programmed. And usually this happens by throwing a lot of data at some learning algorithm that then infers some statistics, and then using these massive amounts of data tries to infer some results. So lots of user data is being thrown into some form of machine learning algorithm that churns through the data, creates a form of model that then queries the corresponding model that has been learned to provide different kind of services. And if you look at pretty much any recent service that you're likely interacting with, there is some machine learning component in the background. For YouTube, what videos are going to be displayed, what comments are going to be highlighted, how ranking is happening, how different comments are being pushed to the front, what videos are being pushed to the main page, but also what videos you are interested in, right? To show you a more personalized option. Same for eBay, right? What kind of advertisements are highlighted, what kind of ads are being pushed. For shopping, Amazon, for LinkedIn, what posts should be displayed for any kind of social media network and whatnot. But also, for example, like you're seeing here the audio recorder, right? Like to improve the audio processing and those kind of aspects, right? So it's pretty much anywhere in any modern applications that you're interacting with requires some form of massive amount of data. It's also becoming quite ubiquitous, right? Any mechanism or any system that you're interacting with has some form of machine learning component, be it traffic management, be it surveillance to some extent in some places, self-driving cars, figuring out traffic patterns, avoiding road closures and whatnot. If you've looked at Google Maps, for example, if you've sent 10 people on a journey to the same location from the same starting point, Google Maps will likely give them different routes as well, right, to kind of balance the load to some extent, leaking some information about potentially where other people are traveling and all these other things. So they have implications between different users and adjustments that they'll need to consider or will have to consider to some extent. If you look at machine learning can be roughly grouped into three major areas: supervised learning, unsupervised learning, and reinforcement learning. All of these three categories have their use. All of them are fairly well defined. You see a lot of research, a lot of uses. We'll mostly focus on the supervised learning approach due to nothing is really established in machine learning. Nothing is really old. It's still a very hyped up field that's under a lot of development. But here at least we have some kind of notion of like some experience. There's for supervised machine learning, there's labeled data. We get direct feedback that we can evaluate. It usually predicts the outcome or the future So for example, estimating the house price. So what is your house actually worth, or your apartment, if you want to sell it? And machine learning will look at, for example, all the recent sales in the neighborhood, previous sales, and then look at a trend and estimate the future price of your house. Right? So most used, and where security has been mostly studied so far. There's been several approaches to try to automate the whole buying, selling, advertising houses approach. And in the US, there's been quite a controversy of automating this across all the different layers. Who's aware of Zillow? Zillow, anyone? 1, 2, 3, a bunch. So Zillow is like a website that tracks houses on the market, their prices, shows listings, shows the different price variations, and also has history. So you can check out how the price of a house has changed over the last 10, 15 years, sellers, the different sellers, the different pictures and whatnot. And there's this interesting, so they predict on how the market will evolve going forward by looking at nearby houses, nearby sales, and then building this estimator for the different price changes. Now, this works reasonably well and gives you an indication, but the valuation of Zillow as a company has also been founded on the fact that they tried to automatically buy for houses when they see a bargain. Now, unfortunately, they don't have everything under control, and there's an interesting security lesson here where somebody trying to sell the house may have more information than that is publicly available, or that is publicly visible to these models. For example, different kind of specific local knowledge about the neighborhood, future plans that are not yet public or not yet ingested into these models. And there's been a couple of interesting issues in the past. If you want to learn more, feel free to search for it. So supervised learning, let's go a bit more into detail what that is. We have a whole bunch of samples, like a whole bunch of examples, such as housing prices. We label them. We extract features, such as the price was this, location was this, crime statistic in this neighborhood is this, flawed likelihood of the area is this. We give it certain labels for each of the features. We throw it into a model, we train, we learn something. This can be any kind of model in the background. And then when we want to know something about, for example, how much is this apartment here worth, we take a sample, we extract the features again, the same features that we trained before, and we make a prediction, right? We give it a label and say this house is going to be worth 50,000, 500,000, 5 million, or whatnot, right? Another example would be a prediction. Like going forward, will this patient need to be hospitalized for longer than a week? For training, we could look at all the patient files, 1 week, like from 1 week before to now, and compare the delta, extract the features. Like 1 week before, the user was coughing, fatigued, had chest pain, had other kind of discomfort, a lot of features that are being extracted and being analyzed. And we know for a fact, right, if you look at past data, how long these people were then hospitalized. We can train a model, and then for a sample, again, we can extract features, analyze it, and then project if this user will be hospitalized for a week, 2 weeks, a month, or so on. Right? So there's an interesting use case that certainly would allow hospitals to better schedule their resources, but there's also a question on what kind of adversarial aspects are there. What do you think an adversary would like to try in this situation? What could they do? Where could we have adversaries? Yeah? Somebody trying to leak the patient data at the far end? Yeah? So you could try to steal information about individuals that the model has been learned on, right? I think that's what you mean. So the model has been trained on actual individuals. The goal is to kind of aggregate information and then make a prediction, but the model could leak information about an individual. Yes, what else? Go ahead. Somebody could lie about their position, so an attacker may want to influence the model and say, yes, this is what it takes to stay longer. Sure, yeah. What else? Good idea. What about another hospital? Like a hospital has spent a lot of money to collect this information, to train this model, right? Another hospital could try to steal it, right? So yeah, there's a bunch of different attack vectors. Steal information, the privacy issue that we had before, steal the model, intellectual property, or alter the output to fool the doctor, for example, to stay longer in the hospital. So I think we had all of these main areas covered, and all of them have different implications. So there's a lot of potential adversaries that we have to protect against in this environment. Today we're going to look at 4 major areas in machine learning security. Model stealing, like trying to recover the model to some extent, right? Getting information back from a machine learning model. Data stealing, trying to figure out the output to recover some kind of internal state or internal information that was used for training. Then altering the output, modifying the output of the model to change the result for some purpose. And we try to be aware of certain biases, like understanding what kind of biases we have when we're looking at massive amounts of data sets. And some biases that we have to carefully avoid when designing a certain machine learning solution. Cool? So let's dive in, and let's start with model stealing, protecting intellectual property in machine learning. And here the idea is that the adversary wants to recover some of the model to replicate certain aspects. Now, there's different kind of attacks depending on how much the attacker knows about the underlying system. It could be opaque box attacks, where the attacker knows pretty much everything. The model architecture and the parameters are not opaque box where the attacker does not know anything, where neither the model architecture nor the parameters are known, and the attacker can only interact with the model by sending a query and then looking at the response. This is the hardest aspect. So it means that it is the most severe attack that would be possible. Gray box attacks are, on the other hand, where the model architecture is known, the parameters are unknown, and the attacker can interact with the model but has information about the type of the model. So it gives the attacker some edge. And this is pretty much the same as if you're looking at fuzzing, right, where the fuzzer gets some kind of feedback from the program execution in these gray box fuzzing approaches if you want to connect to the software testing. And then clear box attacks is the architecture are known, the parameters are known, and the attacker can replicate the model and use the model's internal parameters for the attack to then target very specific information or very specific data. Questions?
When you talk about parameters, are you referring to hyperparameters?
Yeah. Yes. Now, machine learning as a service, that's the example use case that we take, right, for these model stealing attacks. These are usually like somewhere, some entity, such as Amazon, ML, or Google Prediction API, pre-trained some form of classifier using all of their own data that they have collected. So there's some secret training data, there's a classifier, there's a training set, the testing set, everything is being conducted by the provider. The classifier is available as a service for users to query, and the goal would be to charge on a per query basis. Right? So for example, the user makes a query given the profile, the photos, the posts, the metadata of Bob. What kind of person is Bob? Is he more a cat person or a dog person? And the model in the background has looked at all the pictures that Bob posted, and if you see that there's more dog pictures, we would assume that Bob is more a dog person versus cat pictures, right? And it could be the bias thereof. And the goal would be in this environment, without actually having all the details about the model itself, the trained model in the background that potentially extracted a lot of other features. What can we do to query all of these details? Now, the model itself is confidential, given some form of intellectual property that the service doesn't want to leak. And we already know that machine learning models require quite a considerable investment for either the data collection, data acquisition, like getting data could also cost by itself, and then for the training itself, right? For the training, the modern models require quite extensive hardware and quite extensive time. And the goal would be of the attacker to steal the expensive model by simply observing its outputs, right? So for example, just issuing a finite amount of queries would allow the attacker to recover information that is equivalent to the model or equivalent in precision to the underlying model without requiring all the data or the training efforts that have been done before. We're going to be, like as I said, there's not going to be a machine learning class, so we're going to be extremely simple. We're going to look at a linear model where we're just doing a very simple classification. Linear model employs linear function that separates the hyperplane to produce the decision. For example, logistic regression, SVM is a linear kernel. And we have a very simple function. F of x is the parameter w times x plus the constant offset b to move in this hyperplane. If f of x larger than t, then the output class is 1. Otherwise, the output class is 0 in this simple example that we have here. Now, for stealing a linear model, we assume that the adversary knows that the model is a linear architecture, like we're following a gray box model as before, but we don't know the parameters. So assume x is two-dimensional. So we have f of x becomes w1 times x1 plus w2 times x2 plus the offset b. And the adversary wants to steal the parameters w and b. Now, in this situation, how many input-output pairs does the adversary need to observe to steal the model initially? Three? Yes? Why 3? You have 3 unknowns. You do 3 queries. You observe it 3 times. You build a linear equation system. You solve. You get an answer for each of these examples. What if it was d-dimensional? D plus 1, correct. Very good. For 2-dimension, we need 3 queries. For d features, we need d plus 1 to actually build the system and then break this up. So this is so far so simple, right? Or simple enough. Now, this works reasonably well for a linear model. As soon as it becomes nonlinear, it gets quite a bit harder, right? Because we don't really know how the function looks like. The function becomes more difficult to model. Assume the adversary knows the model's architecture. We stay in the gray box model. F of w of x, and the goal would be to steal the parameters w that the attacker would like to know. Now, what we can do is instead, right, we can no longer just do d+1 queries for all the different dimensions. But what we can still do is we can think of it as a fuzzing approach, right? This is why I brought up the example of before. This is a fairly large feature space, an n-dimensional feature space. We just randomly query the feature space and try to have a reasonably good distribution of this feature space. We observe many queries, and then we fit the model on X like any other training data. Right? So we can create a lot of examples and then use these examples that we use to train our own model, which is much simpler to train because we only have to use these examples. Now, unfortunately, this takes quite a bit of queries. For a neural network with 2,000 parameters, we need around 11, in this example, we need around 11,000 queries to get 99.9% similarity. Now, you can, of course, optimize this doing some kind of similar to coverage. You can use feedback. You can bias the creation of the random queries to kind of reduce these numbers a bit. But the underlying issue remains that we still need quite a bit of queries for all the different inputs to have a large enough sample to then retrain and build a similar model. Still, querying a model a couple of thousand times and then retraining is much cheaper than collecting the information, potentially paying for it, processing it, and running the full training efforts and end-to-end. There's different other approaches for stealing neural networks. The location of these hyperplanes to kind of determine the neural network, and you can optimize by kind of guessing how the model is a bit laid out. You can further optimize this depending on your adversarial setting. So you can use this to kind of use the answers to kind of shape your future questions to then guide them in a bit more precise way going forward. Now, the issue here is that in the example, this is from Nicolas Carlini, who is one of the prime adversarial machine learning researchers, and he's been breaking machine learning in all the different configurations. What he looked at, or what they looked at, they extracted a 100,000 parameter neural network trained on this digit recognition, like a simple standard task in machine learning, with 2 to the power of 21.5 queries in under an hour. So this is a very, very interesting feedback here, that observing the output of the neural network does actually reveal its weights and kind of influences the theory of secure inference, so which kind of completely breaks the idea of hiding information in these neural networks. Now, model stealing is somewhat recent, right? The first attack was around 8 years ago, first defense 7 years ago. Well, the idea is same as we've seen with some of the privacy aspects last week, to do some output perturbation, just adding noise to it to reduce the power of the attack. But it kind of, there's this trade-off where you have to be careful to not reduce the accuracy too much. The other option is to detect suspicious queries. For example, collect the number of queries that have been executed, and then try to limit the amount of leakage that you do. There's still changes happening. It's still very recent. It hasn't really been decided yet what the best options are. Takeaways on model stealing, right? Many models are susceptible to stealing. It's a very complex topic. There's lots of concurrent ongoing research, even still. It's a crucial issue for machine learning as a service. So if you build a startup that secretly tries to, where the whole value proposition is that your model will remain secret, you may have to reconsider like how many queries you actually allow, because an attacker could be trying to replicate your models through a certain amount of queries. And you have to figure out some kind of defense mechanisms to protect your intellectual property. Many problems, right? So there's a lot of issues in this area. It's currently a somewhat unsolved field. So as soon as you allow arbitrary queries from an attacker, they will be able to infer certain properties about your model. Especially if you think back to last week again about the privacy implications of accessing certain data sets. And it's similar here with models when you're looking at machine learning. So far, so good. Model stealing from a security perspective, pretty broken. Let's look at the next step, data stealing. And that kind of opens up the issue of privacy challenges in machine learning. Now, we've already seen that for machine learning, we need to train on massive amounts of data. The underlying assumption is that all of the data that is being thrown in kind of like gives us an opportunity to answer certain higher level question, but we are hiding the details about individual users. But this is not always true. Like sometimes the models could be leaking certain aspects about particular input data sets, such as shown in this XKCD here. It's a very active area of research with different kind of attacks being shown again and again. Now, there, as I said, an active research area that tries to limit the amount of exposure. Learning from past failures where this hasn't really worked out in practice. Now, if you look at the privacy risks here in machine learning, right, this can be happening during training and during testing. During training, this could be due to the data used for training, and during testing, the testing data itself, or the actual results might be sensitive as well in this situation. Both could leak certain information. Privacy risk before the machine learning area. Well, before the machine learning area, the issue was potential collection of sensitive personal data, re-identification, inference attacks, and whatnot, similar to what we discussed last week. Now, if you move to machine learning, all of this is being added. Like there's this component in the middle, right, from user data to services, where we now have this machine learning component where the user data is being thrown into these kind of machine learning solutions to extract certain data and add additional features. And we have interesting privacy questions such as, do trained models leak sensitive data? How do they leak sensitive data? And also, like looking back a bit, or taking a step back a bit, can we train good privacy-preserving models that don't leak data? And if so, how would this be possible? Now, a typical task that we use in machine learning, or where machine learning is used, is classification. Is the current image, for example, or what type is the current image, right? So the input data set will be a large set of images. The training data set, the model is being trained. And then for the query, the model is being queried again with a prediction with a certain list of classes and probabilities. The prediction says, oh, this could be a plane, this could be a ship, this could be a truck, or it could be an automobile. And the highest prediction would be for automobile, and here in this example, this would be true. So far, so good. So the prediction here would be correct. Now, this already could leak what kind of, like depending if you can query different kind of cars, this could leak certain information about the input training set that has been used and whatnot. So as an attacker, you may want to understand or infer which data was used or not used to train the model. And with that, the attacker could query different kind of data sets. So there's a population of sensitive data, for example, and reference data, and some of which may overlap, and the attacker can play with the differences. Now, with pictures of cars, this may not be as privacy sensitive, but if you think again about medical record, if your medical record was included in the training or not, it again becomes a bit more sensitive if you can infer that this was done in here or not. So the query would be, was the user X in the sensitive data set or not, to infer the presence. So think of it as membership inference in the private set or not. So the attacker may know the reference data and tries to infer if the sensitive data was part or not. Now again, we're using a gray box attack, no knowledge of the model parameters. There's some training data that has been used to train a machine learning model, and we try to work through that. The data is being moved into the training API, the model is being trained, and we can then query. Right? So here, a simple example would be an input from the training set. We get a classification, and we get a distribution of weights. If we send an image from the training set. If we send an image not from the training set, we get a slightly different classification with slight perturbations, and then the attacker tries to figure out the difference between the two distributions to infer some details about the underlying input data set that was used. Now what we can do is, right, so this is a simple example, input from the training set, input not from the training set, both queries are being sent by the attacker. We can kind of automate this and then train a model to recognize the underlying difference. So here the idea is that we leverage public data for the training as we're building up this information as the attacker, and then we compare and start querying the internal model and then trying to figure out the differences. Okay. So let's assume we don't have samples of the training data. So no knowledge of the model parameters. So what we can do is, instead of using the data set that we have, is we can try to create the shadow of the actual model to understand how it behaves. So we can create a first shadow model, use this to test, see the quality of results that we get. Then a second shadow model, third, fourth, fifth, and so on. So the idea here is we've got this target model up there, and we try to infer like what kind of data was actually used to train this target model here. And in this attack here, right, so we want to know like what input has been used in this target model. Okay? So we create a first shadow model where we try to use some data set, and then we query our model, the target model, and look for differences. If it looks good, we know we have the right data set. If not, we slightly adjust and then move on to the next shadow model and improve step by step to then figure out what the original training set actually was. So similar here, we've got the training set was used for the training API, and then in the prediction API, we can do this inference attack to again figure out what was this record in the training set or not. Now, in this example here, this is a simple query, a simple attack where the certain set of customers are being mapped, and we see that the accuracy of the attack is reasonably large. So we kind of leverage the data distributions for training, and we again compare getting some kind of feedback in this this example. So we don't actually need the data set and can use this for training and then for the attack. So far so good. Let's assume we don't have knowledge of the underlying distribution of the training data, right? So we're removing one additional piece of information. Like before, we didn't have samples of the training data. We just used the queries to train different kind of models and therefore infer the underlying models. Now we go one step further and we assume we don't know the distribution of the underlying training data, right? So first attack was we used training data, public training data. Then we queried the model to figure out how the training data look like. And now we don't even know the underlying distribution of the training data as the third step. And we're using this for to infer an additional shadow model by training a model using random data, and then again comparing the differences between the two types of queries by querying our model and the target model multiple times. And as we see, we can then shift the distribution of this random data to get better models that in the end get us closer to the target data. This is again a task that is being repeated multiple times until we get close enough to the real data for the attack. So here, the attack is we use random data for training. We compare the two outcomes and then iterate. So again, we are getting closer to the underlying hidden trained model that we're trying to infer. And then again, we know how the sample distribution somewhat look like. Now, the question you might ask is, why do these attacks work? Because the model that was originally trained from the original data that we would like to know through the training API kind of overfits the target data. And now this overfitting is the common issue, both for privacy and for learning. For privacy, does the model leak information about the data in the training set? Versus for learning, does the model generalize to data outside the training set? And there, this overfitting of the model kind of overgeneralizes and then thereby leaks some information in that regard. To improve, right, we need to reduce the overfitting. Overfitted models leak training data because they are kind of overfitting to certain samples, but they also lack predictive power. So the solution to this would be to increase the granularity of the underlying model to thereby reduce the overfitting, allowing the attack or restricting how the attacker can actually get information. Now, as a quick summary of this, some takeaways on the machine learning privacy issues. Again, many problems, some initial steps. It's a very young field on leaking information. There's still inference attacks, still kind of potential for leakage. And you have to be very careful when you're training a model using some form of private data that you're leaking some kind of internal state to the attacker, as the attacker can issue many queries on that. So data stealing is a common issue, especially when you see machine learning models being used in certain environments. So you have to be a bit careful on adjusting this on a particular basis, especially if adversaries can issue arbitrary queries. And I think we're going to take a break here. So we talked about model stealing before, right? So adversaries that can steal the underlying model by issuing a certain amount of queries, enough queries to get a shadow model to some extent. And we've looked at data stealing, where the adversary can learn what kind of data was used to train, or even figuring out individual data sets, or if individual data set data samples were used in the creation of the model or not by alternating the different model creations. As said, we're going to take a break here. We're going to continue quarter past to talk about output altering and then biases. Thank you for all these questions. I really appreciate them. Hopefully I was able to clarify. Let me quickly repeat the high-level questions that were raised during the break, because I think some of them helped with the understanding. So for model stealing, again, the idea is that we want to recover the model without having to retrain everything. So we want to recover the model for cheap, essentially, without acquiring the data, without actually having the data or having access to the data, and without having to do a full end-to-end training. Usually this works because the training set, the training data, is much more complex than the resulting model. So we can issue much fewer requests to recover all the information that are captured by the model itself and thereby extract it that way. So with fewer queries to the trained model, we can infer some kind of shadow information that is sufficient to train a model that is behaving roughly the same. Right? So think of this as an approximation and getting an understanding of how much the model actually knows. For data stealing, now the second part that we looked at, the idea is that we want to know if certain information is in the data set that was used during training. And either we have an example data set in the first attack, we know what a reference data set could actually look like, and we're trying to infer certain aspects. Then we generalize that in two additional steps to kind of make this more and more random, step by step, where in the end, in the third step, we're only sending random data into the training and then refining this again and again to infer if certain aspects or certain, for example, patient information has been used in the training data set, recovering these details. We're now going to move on to the next step, altering the actual output that was used. Now, this is an interesting angle where people try to make machine learning fail, right? So by sending certain queries to a machine learning system, the attacker is trying to influence the outcome of the machine learning system. So in this example here, right, the machine learning system, by looking at the picture on the left, would classify this animal as a panda. And it's a typical example in adversarial machine learning that I'm sure all of you have seen about 15,000 times. If you only add a little bit of noise, right, just a little bit of random noise, the machine learning classifier will classify this as gibbon, like a monkey, right? So the idea here is that the attacker has a little bit of control to modify the color values of the original image to then massively modify the output of the classifier. So inputs to a model that an attacker has designed to cause the model to make a mistake. So the goal is that instead of doing the right classification, that, for example, a human would say this is a panda, the model says something different. So slight modifications cause a massive effect for the model that would then invalidate or cause the model to give an incorrect answer. So the issue here is that the input, the assumption of independent and identically distributed no longer holds. As in, this is not a random image that we're trying to classify, but the attacker can kind of probe and test the model to create an image that gets us, or to create a distribution matrix that gets the attacker the desired effect. It's no longer identical because the inputs are intentionally manipulated to not belong to the training distribution, right? So the attacker potentially figures out what the training distribution looks like, either by looking at the training data itself or by multiple queries through the model. And then independence. Inputs are no longer drawn independently. The attacker may sample from a single input repeatedly, trying to push it outside of the boundaries. Right? So the idea here is that the attacker kind of pushes the model to the limits and then beyond the limits so that it misclassifies. And the attacker has control of the input. Right? The attacker can modify any arbitrary pixel. And depending on the adversarial game that we are playing, the attacker gets control over a couple of pixels. So the attacker can take one picture that is already, like where the model would already have difficulties to classify it as a panda, and then push it over to another target. Quick refresher. The idea is to find the model parameters that minimize the empirical loss. So there's the data distribution for the set of example images that we have in our training data set, minimize the loss and minimize the error in classification. So we've got this labeled data set of images. We're training all these images. The model tries to extract during learning the best kind of distribution to minimize the overall loss over through all the data sets. We're training those weights by using a simplified or some flavor of gradient descent, where each learning step slightly refines the weights to make sure that we are as close to this best possible distribution as possible. Now, during training, this happens in push. We are adjusting the weights based on all the input data sets, the input images that we have in this example. And then we can adjust this in each learning step until the delta between one learning step to the next is small enough that we consider training to be complete. Now, the adversary tries to find some kind of noise that is overlaid over a target image or that of their choosing that maximizes the loss. Right? So the idea here is how can we find like what pixels do we need to modify to maximize the loss that it still looks the same image but pushes the classifier outside of its boundaries. Now, so the idea is that if we change x plus this delta that maximizes the loss, it still looks similar to the original x. And similarity here means to some extent some change that cannot be perceived by a human. Right? So some kind of difference that we no longer we don't immediately recognize. So maybe we see a couple of pixels that are off, slight colors that are off, but we as humans would still classify this as the panda, for example. Right? How to define similarity? It's often represented as adversarial cost, and usually in the attacker model defined as how much an attacker is allowed to modify. If the goal is to be not perceivable, the common cost is a norm or perturbation to some extent, as in a budget, a kind of epsilon that the attacker is allowed to change a given target to push it a certain amount out of the target area. Is this a good constraint for adversarial examples? Now, the norm here is like how many pixels are being changed by what kind of color value and what the example is. Here, in the panda example, in this initial example, the norm was the full set of pixels, and each pixel has been changed a little bit to then push the model as much as possible. So that's one example, right? Here, as mentioned, in this original adversarial machine learning example, each pixel has been adjusted to then create the desired effect. There's other similarity relations that are possible, right? So it could be a small, for the dog, right? A small perturbation of the image itself, or like changing a part of the image by adding the strawberry there. Or alternatively, the perturbation could also be a slight twist, right? For example, for the original training, this image was used, but if you just tilt it a bit, it can result in a completely different image. And the adversary may be like rotating, flipping, changing colors and whatnot to do certain changes. We humans would likely, most humans would consider the two images very similar because they're only rotated. Same for above. Most humans would consider the images very similar except for like a small change. But for a machine learning model, this can massively push the understanding. Because a machine learning model does not look at the image like we humans, but it will concentrate on certain features, right, that it decided on during the training. And the features are very different for a machine learning model from human perception. Attacks also don't always have to be imperceptible, right? So for example, in this set of pictures here, Reese Witherspoon is being classified with a set of glasses as as Russell Crowe on the right-hand side, and we kind of see that there's like she has a bunch, like a set of glasses overall, and very likely the machine learning classifier just concentrates on a couple of pictures, right? It learned that a couple of pixels somewhere around the eyes are most distinctive to recognize an actor, and maybe like overfit on the eyebrows of Russell Crowe, and by changing those exact pixels with this funky image, funky set of glasses that has been overlaid, it pushes the classifier to decide, hey, this is Russell Crowe and not Reese Witherspoon, right? So there's different set of perturbations. The rest of the image remains the same, and only some of them are being changed. Still surprising, but also interesting to see. Now, oddly, or not oddly, interestingly, adversarial examples are transferable. So many of them have a transferability property. Samples crafted to mislead a model A likely also mislead a model B, which means that these adversarial examples are somewhat universal. If the models have been trained using similar data set, then the adversarial example will not just work on one model, but also on another model that has been trained on a slightly different data set. Which means that an attacker can train locally and create an attack locally to then fool the attack online, right? So this gives the attacker an edge to be able to train ahead of time using the local data set to then run it remotely. Like for example, the confusing stop sign with a no truck sign, right? Which could be an interesting attack for a camera in a car. So a car, instead of detecting a stop sign, would detect, hey, this is just a no trucks down this road sign, and happily continue without stopping, and thereby causing an accident. Also, interestingly, it is often possible to construct a single perturbation that will fool a model when added to any image. So attackers need only minimal resources to attack the system. So from banana to truck, from cat to hammer, from dog to football, with only a very slight change. So in this example here, the attackers created this image. It's like they printed this as a little sticker that you could slap on any surface, and then the classifier would instead classify this not as banana but as a toaster, only because this little sticker was somewhere on either on the image itself or like even slapped somewhere on. And this used to be a fun game a couple of years ago, where people printed these stickers to confuse the different classifiers that have been trained. Interestingly, also the attack, the model is like 98% certain that this is a toaster, right? Which to us humans, it doesn't really look like a toaster, but it triggered the model to lock in this area. Which all of these attack examples beg the question, how can we defend against adversarial examples, right? So if you recall the machine learning training objective, right, we're trying to minimize loss across all the images that we train. How can we defend against adversarial samples? Any ideas? Yeah?
Try to minimize the loss in a small area around the example so that even if there is a small population, the model should be able to recognize that particular sample.
How would you define the area around the example?
Like you could have a small delta,
Uh-huh.
and then you consider samples in, for example, a sphere around that particular example, and you do this for all examples.
Yep. Can you generalize your technique? Like your proposal was you take all of the image data and then you create perturbations of these image data to then train the model around these image data. Because already you have labeled training data and you just multiply the training data for each of the training samples that you have. You create a couple of thousand images with slight potentially adversarial perturbations, right? So essentially you run an attack yourself. But you run the attack during training, you create all these adversarial examples, and then you kind of train the model not just on the target examples that you have, but under all the adversarial examples as well. So the standard way, as we've just determined, is some form of adversarial training or leveraging some robust optimization by creating additional examples and thereby doing the perturbations ourselves to then ensure that we can mitigate these effects. Preventing adversarial examples looks at the idea that, hey, as orthogonally we can look at what data we have been what the model has been trained on, and then detecting that something is outside of the comfort zone of the model. That's another robustness measurement, right? So the idea here is with this extension, certified defenses, is that the model is detect, hey, this has not been part of the training data set, therefore I don't give an answer. Like, so this would be a two-layered approach where the first model decides, has something like this been in the training set, yes or no? If not, then go on, otherwise do the classification. Yes?
In your example, I don't really understand how this attack impacts someone else in the attacker. Like the attacker can send an image and it doesn't predict well.
Let me go back here. That's an excellent question. I'm going to refer to the stop sign or no truck sign. Like, I'm an attacker, I slam a picture on a stop image, and all the Teslas zoom by and crash into the wall. It's not just me that's being affected, right? So that's one example. But what else could you do? What's another good example? Any other good examples? Like, I'm blanking. Go ahead. Malware detection. If somebody wants to hide, maybe. I'm not sure how much machine learning is being used. They will likely do binary similarity. Yeah. Go ahead. Insurance fraud, right? I want to, like, I dropped my camera. I now want to get 15,000 from the insurance company and make sure that, yeah, that could be an example.
Antiviruses is a really certain example for certain type of antiviruses which made to detect anomalies, and they're mostly built from AI.
Oh, you mean anomaly-based detection?
Yeah.
Sure. I thought more looking, maybe I misunderstood you. I thought more looking, analyzing the machine code to some extent, but if you look at the behavior, yeah, I could see the case. Sorry, maybe I misunderstood. Go ahead. Yeah, jailbreak large language models, leak training data, for example. But that goes back to the, yeah. Cool. Does that answer your question? Very nice, good question. So if something is not clear, ask. Certified defenses, again, let's go back here, tries to teach the machine learning model if something is in scope or not. Right, giving it the power not to guess if something is outside of the training set, but to decide. The other one is just think of it as rate limiting ++, detecting suspicious queries, analyzing, does this query look malicious or not? And thereby, as a heuristic, infer if an attack is happening or not. Attackers are not restricted to computer vision, right? So it's not just images, it's also text. For example, for text classification, with only changing a few words, you can go from a model thinking that it's a negative tweet to a positive tweet, for example, for bot detection or whatnot. So yeah, there's slight perturbations that also have big effect on text. The mood detection, the topic detection, all of these can be changed quite easily if the attacker knows the model well enough or the target well enough. So takeaways on these adversarial examples, it's that protecting machine learning against output alteration by these adversarial examples is really, really hard and pretty much an unsolved problem for now. If the adversary controls the inputs in the deployed models, they pretty much always win. And it's unclear whether there will ever be effective defenses because of the infinitely large feature space. It's a high-dimensional space. It's very difficult to characterize, and it's very easy to fool the model. Adversarial training, as what we discussed, creating a lot of similar images is the most promising protection technique, as we are trying to expand the set of good examples to then kind of prohibit against malicious modifications. But it also has its limits, because an adversary can also try to understand how far we pushed our adversarial learning and where the gaps in the model actually are. If adversarial examples can occur for an ML usage that you're considering, be careful, as this can create very severe vulnerabilities. So be careful what you're deploying. So far, so good. We're going to move to the last topic for today, biases and fallacies. And it's one of my, we're going to talk about some of the potential fallacies in machine learning. The data set is often not as evenly distributed as we would like. For example, if you use the training data set, some samples may be used more often than not, and that can lead to interesting issues and challenges when working with these data sets. And one of the big issues that we're going to look at, I think I've mentioned this once before, is the base rate fallacy. We humans, we usually assume equal distribution of cases. If they're not, we very falsely interpret the result. So, for example, if you see that more vaccinated people were hospitalized during COVID-19 than unvaccinated people, you would assume that the vaccines are not effective, because you see more vaccinated people are in the hospital than unvaccinated people. The underlying assumption is that the number of vaccinated people equals the number of unvaccinated people. But essentially, right, the number of hospitalized people cross-cuts between the two groups. So it will, a much larger number of unvaccinated people out of the set of unvaccinated people will be hospitalized than vaccinated people. But because the 95% of people are vaccinated, obviously some of them will end up in the hospital because maybe the vaccine was not effective for them, or the vaccine only reduced the impact of the infection, right? So essentially the true hospitalization rate is 5 times higher in the unvaccinated population. So 50% of the unvaccinated population versus 10% of the vaccinated population, which is a massive difference, right? But if you look just at the numbers, it looks as if there's more vaccinated. The vaccine itself would not be useful. So, for example, this base rate fallacy or prosecutor's fallacy has effects in many different places, such as like if you look at performance metrics for hate speech detection. We initially would assume that tweets that are hate speech are roughly, there's the same amount of tweets that are not hate speech. So we can look and break this into, when we're designing a machine learning system that tries to detect hate speech, we can break this into a set of 4 different classes. There's tweets that are hate speech, and the prediction is hate speech, then there's true positives. Prediction that it's not hate speech, but it is hate speech, the red one, is a false negative, right? Instead of the first one was a true positive. Prediction not hate speech in the green is a true negative, so this is correct. And prediction in the dark green, the tweets that are not hate speech that are classified as hate speech is a false positive. Now obviously for our classifier we want to have as high as possible true positives and true negatives, and as low as possible false negatives and false positives. Now the issue here is that we face that the set of hate speech, except for at least on Twitter a couple of years ago, was much lower than the number of tweets that are not hate speech, right? So the classifier, if there were a bunch of false positives, right, 0.001% false positive, already results in a massive amount of tweets being flagged, right? So even if you have a very low false positive number, this would result in a massive amount of tweets being flagged. And the same is true when we talked about network intrusion detection. Most of the packets are benign. So even a very low false positive rate results in a massive amount of alerts that are using up a lot of resources. So we kind of have to be aware of these differences in the underlying data distribution and consider those when designing the mechanisms. So for example, there's a machine learning solution that looked at the accuracy on on some easy pilot whatever benchmark on the correctness of the like facial analysis, like how well it recovered features or whatnot. And the issue is it works really, really well on like Caucasian males. Very likely because the data set contained about 98% of images of Caucasian males. It worked reasonably well on like if you split based on gender, darker males. So there's a strong bias in the original data set versus towards males, and an even stronger one towards female. And then if you combine the two, darker females was the worst performing set, likely because they were massively underrepresented in the data set. That's also an issue when we're looking at medicine. right? If you consider the modern medicine, the vast majority of studies has been done on males. There's another part of the population that is massively underrepresented in many of these trials, and we're just lacking the underlying data to do that. And this calls for additional data collection to complement and to create better results. Now, one of the issues here is, the next issue or the next bias with machine learning. Let's say we have a classification task. Should we send a patient with bronchitis home? Will they be safe? We can do a rule-based analysis, based on previous samples. If X, then Y. Right? We encode this. If they have this, this, and this feature, we looked at this. It makes sense. We sent them home. This results in human-readable rules. The causation is very intrinsic. We can understand this will result in this effect. We'll send them home. Everything is good. Now, the accuracy is rather low because we don't have access to all the data. We don't have a perfect prediction. Machine learning often results in better accuracy because you can leverage all the secondary features, secondary insights through the massive data sets that are there. But then, unfortunately, it's not immediately possible to understand why a decision is made. And this requires us to kind of understand, when we're designing machine learning solutions from a security perspective, to reason about all the biases we may or may not have. Because we may be sampling in a distribution that we don't fully control. And we have to understand what the limitations of this reasoning are. Are we ignoring a part of the population when we're making the results? Do we need to adjust for that? Right? Is our data set, the data distribution, reasonable enough? Right? So we need to figure out how what aspects we're actually missing. There's also potential controversial machine learning research. So this example here, some researchers trained to decide, given an image, is the person gay or not? Right? Which is rather controversial. Not everybody wants to share their sexual preferences with everybody outside. It's also a very private topic. Now, the algorithm clearly learned. What do you want to share? The algorithm clearly learned something, right? Based on the original data set. Now, what did it learn? Is it the pose? Is it the part of the face or whatnot? What do we want this information to be shared? Do we want these data sets to be collected that could then infer information about others that may not want to share, right? Another problem we're facing is reinforcement. We may be locked into some constellation of some feedback loop that we already have, which then kind of reinforces the underlying issues. And one of the prime examples here is crime and crime statistics. For example, in a city, the crime statistics could be distributed and analyzed, and then, for example, you send more police to areas where you have reported crime. And this results in police finding more and recovering more of these details, thereby further increasing police presence in these areas, further increasing the pressure on these communities, right? So these effects are these reinforcement of the underlying bias that results in huge issues in the way resources are allocated. And again, we have to be aware of the biases we are having and we are looking at. There's different types of biases as well. Statistical bias, difference between, for example, an estimator expected value and the true value. Group fairness, the outcome should not differ between demographic groups, individual fairness, whatnot, right? There's a lot of different fairness approaches. There's a bunch of interesting tests that you can do about your own biases that if you haven't done so already, I highly encourage you to try. You'll learn a lot about yourself and what kind of implicit biases you actually have, because all of us, we have our biases. And before you start reasoning and building machine learning system, it may be great to learn about your biases as well. So if you take that from this class, this may also be an interesting angle. Now, takeaways on these biases and fallacies. Deploying machine learning is hard. Reality differs from lab conditions. In the lab, you can sample a very small, well-known distribution, but you have to, when you deploy this to reality, you have to be aware of if this actually matters, if this fits the reality. There's the base rate, right? You have to figure out what the real distributions look like, and then, yeah, classify the different biases that you have, as I mentioned. Now, machine learning exposes subtle security and privacy challenges that when designing and working with these systems you have to be aware of. You have to classify it, you have to document them, and especially as the outcome is not rule-based, you have to be very much aware of them to not fall into these pitfalls. We've gone through 4 examples. Adversaries may steal the models, may steal data from models by simply querying them. Models themselves may leak private information about the training set in the 3 examples that we've gone through. Adversaries may trick the model to give wrong results and push classification into different areas. And also protection against all of these different attacks are hard, and many different biases and pitfalls exist. That's all that I had for machine learning for today. Next week, we're going to have the last quiz, and we're going to follow the quiz with a short summary and then kind of a reflection on the class. So I'm going to see you one more time next week. The video should be online hopefully soon as the recording finishes. If there's any questions, I'll stick around for a bit. Otherwise, I'll see you again next week. Thank you.